What if everything you've learned about how our solar system moves through space is completely wrong? You've seen the diagrams in textbooks. Perhaps you've watched those mesmerizing animations showing our solar system spiraling through the galaxy like a cosmic vortex. Beautiful, isn't it? But here's the uncomfortable truth. Reality is far more complex, far more mysterious, and infinitely more fascinating than those simplified models suggest. The solar system isn't just a neat collection of planets circling a stationary sun. The sun itself dances through space, pulled by the massive gravitational embrace of Jupiter and Saturn. Meanwhile, our entire solar system slices through the Milky Way at a dramatic 60-degree angle, like a disk cutting through cosmic waters. But wait, that's just the beginning of this mind-bending journey. Because what we're about to explore will fundamentally change how you perceive our place in the universe. Think of the Milky Way as a living, breathing organism. Within its spiral arms, hundreds of billions of stars swirl in an intricate ballet. Our solar system isn't exempt from this dance. In fact, it's one of the performers, though not the one you might expect. As we orbit the galactic center, we don't follow a simple circular path. Instead, imagine a wave. Our solar system bobs up and down through the galactic plane, oscillating vertically like a cork on ocean waves. This vertical motion isn't random chaos. It's the result of gravitational interactions with the dense disk of matter that forms the Milky Way's main structure. But here's where it gets truly cosmic. The Milky Way itself isn't standing still. Our entire galaxy is being pulled toward massive structures in space. The local group, which includes Andromeda and dozens of smaller galaxies. And the local group, it's being drawn toward even larger galaxy clusters, in a cosmic hierarchy that seems to have no end. Each layer of motion builds upon the last, creating a trajectory so complex that it defies simple visualization. We're not just moving through space, we're surfing on gravitational waves created by the universe's largest structures. Now, here's a question that might make your brain itch. Is any of this motion actually real? Picture yourself on a high-speed train. You toss an apple straight up, and to you, it rises and falls in a perfect vertical line. But to someone standing on the platform watching your train rush by, that apple traces a parabolic curve through space. Same apple, same toss. Completely different observed motion. This is Galilean relativity in action, and it reveals something profound. Motion is relative to the observer. The laws of physics remain constant, but the motion you observe depends entirely on your frame of reference. Apply this principle to our solar system, and the implications are staggering. From Earth's perspective, ignoring external gravitational influences, we trace elliptical orbits around a relatively stationary sun. But zoom out to a galactic viewpoint, and suddenly, we're careening through space in a complex helical pattern, oscillating above and below the galactic plane. Take it one step further. Imagine you're in a spacecraft traveling at exactly the same velocity and direction as our solar system. From your perspective, the entire solar system would appear completely stationary, frozen in space. So which view is correct? The answer is both humbling and liberating. They all are. Motion isn't absolute, it's a relationship between observer and observed. This raises a fascinating question. How did humanity, bound to a single planet in this cosmic whirlwind, ever figure any of this out? For millennia, humans looked up at the night sky and wondered. But it wasn't until the 16th century that we began to piece together the puzzle of celestial mechanics. Nicolaus Copernicus revolutionized our worldview by placing the sun at the center of our cosmic neighborhood, with planets tracing orderly orbits in a nearly flat plane. This Copernican model shattered the Earth-centered view that had dominated for over 1,000 years. But Copernicus was just the beginning. Enter Johannes Kepler, a mathematical genius who discovered that planetary orbits aren't perfect circles, they're ellipses. More than that, Kepler revealed 3 elegant laws that govern planetary motion. First law, planets orbit the sun in elliptical paths, with the sun positioned at one focus of the ellipse, not at the center. Second law, planet sweeps out equal areas in equal times. Translation: Planets move faster when closer to the sun and slower when farther away, like a cosmic roller coaster. Third law, there's a precise mathematical relationship between a planet's orbital period and its distance from the sun. Specifically, the square of the orbital period is proportional to the cube of the average distance. This reveals a deep mathematical harmony underlying planetary motion. Kepler's laws were descriptive, they told us what planets do, but the why remained elusive. Until one man changed everything. Isaac Newton didn't just explain planetary motion, he revealed one of the universe's fundamental forces. His law of universal gravitation states that every object with mass attracts every other object with mass. The strength of this attraction follows an elegant formula: F equals G, mm. Let's decode this cosmic equation. F is the gravitational force between two objects, is the gravitational constant, a fundamental number woven into the fabric of reality, and m are the masses of the two objects, is the distance between their centers. The implications are profound. Gravitational force increases with mass. Jupiter pulls harder than Mars because it's more massive. But gravity also weakens dramatically with distance. Following an inverse square law, double the distance, and gravity becomes 1/4 as strong. This reveals why planets maintain stable orbits. Each planet must move at precisely the right speed, fast enough to avoid spiraling into the sun, but slow enough to avoid escaping into interstellar space. Earth, for instance, hurtles through its orbit at approximately 30 kilometers per second. Inner planets race faster. Outer planets cruise more slowly, each finding its gravitational sweet spot. Newton's theory also introduced a concept that would prove crucial to understanding our solar system's true motion: the barycenter, the center of mass around which multiple objects orbit. This wasn't just theoretical elegance, it was the key to unlocking the sun's hidden dance. Here's something they probably didn't teach you in school. The sun doesn't sit still at the center of the solar system. It actually wobbles. The barycenter, the gravitational center of mass for the entire solar system, isn't fixed at the sun's core. Instead, it shifts constantly based on the positions of the planets, particularly the gas giants Jupiter and Saturn. When Jupiter and Saturn align on the same side of the solar system, their combined gravitational influence is so powerful that the barycenter can shift to a point outside the sun's visible surface. Think about that. The sun, containing 99.86% of the solar system's mass, still gets pulled around by its planetary companions. This cosmic tug-of-war creates a complex wobble in the sun's position, which in turn affects the trajectories of all the planets. It's a gravitational symphony where every object influences every other object, creating patterns within patterns. Understanding this barycentric motion was crucial for 19th century astronomers who were beginning to map the solar system's place within the larger galaxy. But they needed new tools that could measure the vast distances between stars and detect the subtle motions of celestial objects. In 1838, Friedrich Bessel achieved a breakthrough that would change astronomy forever. He successfully measured stellar parallax for the first time. By observing how a star's apparent position shifted when viewed from different points in Earth's orbit, Bessel could calculate its distance using simple trigonometry. This technique provided astronomers with a cosmic ruler, allowing them to map the three-dimensional structure of our stellar neighborhood and ultimately determine our solar system's position and motion within the Milky Way. 4 years after Bessel's parallax measurements, Christian Doppler introduced a concept that would become one of astrophysics' most powerful tools: the Doppler effect. You've experienced the Doppler effect with sound, the way an ambulance siren's pitch changes as it passes you. But Doppler realized this principle applies to light as well, and the implications for astronomy are extraordinary. When a star or galaxy moves toward us, its light waves compress, shifting toward shorter, bluer wavelengths. We call this blue shift. When an object moves away, its light waves stretch toward longer, redder wavelengths. This is redshift. By analyzing these spectral shifts, astronomers can measure the velocity of celestial objects with remarkable precision. This technique allows us to determine whether we're approaching or receding from specific regions of the galaxy, helping us trace our solar system's orbit around the Milky Way. The 20th century brought even more revolutionary discoveries. Edwin Hubble, using the massive Hooker telescope at Mount Wilson Observatory, discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This observation led to the concept of the expanding universe, fundamentally changing our cosmic perspective. Meanwhile, Carl Yansky, investigating radio interference for Bell Telephone Laboratories, made an unexpected discovery: radio waves emanating from the Milky Way. This finding opened an entirely new window into the universe and helped astronomers map the distribution of mass within our galaxy, including regions obscured by dust clouds that block visible light. Yansky's radio observations revealed that the Milky Way's mass isn't uniformly distributed. Dense regions of matter, strong magnetic fields, and concentrated stars create gravitational landscapes that influence everything moving through them, including our solar system. This explained why our solar system oscillates vertically as it orbits the galactic center. We're responding to the gravitational terrain of the galaxy itself, riding the ripples in the Milky Way's gravitational field. The launch of Voyager 1 and Voyager 2 in 1977 provided the first direct evidence of these theoretical models. As these intrepid probes ventured to the outer planets and beyond, their measurements confirmed the complex gravitational forces shaping our solar system's motion through the galaxy. But just as some answers emerged, new mysteries deepened. In the 1970s, astronomer Vera Rubin made observations that would shake the foundations of astrophysics. She studied the rotation curves of galaxies, measuring how fast stars orbit around galactic centers at various distances. According to Newtonian gravity and our understanding of visible matter, stars farther from a galaxy's center should orbit more slowly, just as outer planets in our solar system move more leisurely than inner ones. But Rubin discovered something shocking. Stars in the outer regions of galaxies were moving just as fast as those near the center. This shouldn't be possible unless there's far more matter in galaxies than we can see. This revelation led to the concept of dark matter, an invisible form of matter that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet dark matter's gravitational influence is undeniable. Scientists now believe that dark matter forms massive halos around galaxies, providing the additional gravitational glue necessary to hold them together. For our solar system, this means we're not just orbiting through empty space between stars. We're moving through an invisible ocean of dark matter, and its gravitational influence subtly shapes our trajectory. As we complete our 2 to 5 million-year orbit around the galactic center, we're constantly interacting with this mysterious substance. But how dark matter interacts with ordinary matter remains one of physics' greatest unsolved puzzles. We can measure its gravitational effects, but we cannot directly detect it. We know it's there, which describes gravity, touch, or fully understand it. Similarly, Einstein's theory of general relativity as the curvature of spacetime works brilliantly for most situations. But in extreme conditions, such as near black holes or during the first moments after the Big Bang, our theories face challenges. Reconciling quantum mechanics with general relativity remains one of the most significant challenges in modern physics. The motion of our solar system through space is influenced by forces we're only beginning to comprehend. Dark matter, dark energy, gravitational waves, and the fundamental nature of spacetime itself, these are the frontiers of current research, shaping scientific inquiry in the 21st century. Our journey from Copernicus's sun-centered model to our current understanding of dark matter halos spans centuries of human ingenuity, curiosity, and persistence. We've discovered that our solar system isn't simply orbiting in a flat plane, it's surfing through a dynamic, three-dimensional galaxy, influenced by visible and invisible forces alike. And yet, despite all we've learned, the universe continues to surprise us. Each answer reveals new questions. Each discovery opens new mysteries. The solar system's true motion through space is more complex, more beautiful, and more mysterious than we ever imagined. So the next time you look up at the night sky, remember, You're not standing still. You're on a planet orbiting a wobbling star, which is bobbing up and down through a galaxy, which is racing toward other galaxies, all while surrounded by an invisible ocean of dark matter. We're only beginning to understand. If this cosmic journey expanded your perspective on our place in the universe, show your support by hitting that like button and sharing this video with fellow space enthusiasts. And if you want to continue exploring the mysteries of our universe, subscribe to Brightbounds, where we illuminate the boundaries of human knowledge and venture beyond. The universe is vast, mysterious, and waiting to be understood. Join us on this journey. Brightbounds, exploring the universe, one discovery at a time.